Last week we talked about the Heaviside function, and sometimes you will see this is also called unit step function. Okay, for this spatial function, I only turn on when t is greater than 0, and the value is always 1. Otherwise, it is always off. Okay, and then we also can shift this unit step function. If I shift by a, that means before a, when the time is less than a, there'll be always 0. But when it is above a, they will activate the system or the device, so it becomes 1. And you will see the difference between the function times the shifted Heaviside function. And also, if I shift my function times the shifted Heaviside function, you can see the difference. For this example, if I just time the shifted Heaviside function, then I will have a jump at that point when you want to turn on or turn off. But if I also shift the function myself, then this overall function is smoothly at a. Next, what is the Laplace transform of this function? And the textbook said that this is the second shifting theory. Okay, if I want to find the Laplace transform, when I shift already, and I also times the shifted Heaviside function, then what happens here? You will see that I have the Fourier transform, but now I times the e to the a minus as, this exponential term. We can just use the definition of a Laplace transform to find this function. So first, we know that this is integration, and e to the minus st times this function. And this is the integration from 0 to infinity. I can take it as two parts. First, I will take it the integration from 0 to a. And then the second part of the integration will be a to infinity. Okay. Then the first part, what is the integration for the first part? Zero, right? Why is it 0? Because the shifted Heaviside function. Because when t is less than a, this shifted Heaviside function is 0. So that's why the integration is 0. And how about the second part? The second part, this is 1. Right, because when t is greater than a, this shifted Heaviside function is 1. So I only have this part. I need to take the integration. And then since here I have a t minus a, so I would like to change the variable. So here, if I change the variable, so tau equals t minus a. That means d tau will be equal to dt. And t becomes tau plus a. and then the Laplace transform becomes e to the minus st. T now becomes tau plus a, f of tau d tau. Let's rearrange it. Put the e to the minus as outside because there's no tau here. And then I do the integration. E to the minus s tau, f of tau d tau. So that's why this is the exponential term times the Fourier transform. Okay. And here's a note. Then actually what is the Laplace transform of a shifted Heaviside function? You can also think about this. Okay. But you say that, well, I don't have function f. Think about the function f is 1. So if we check the table, 1, the Fourier transform is 1 over s. Okay. And this is a constant, right? O constant. So if I shift, I still have 1. So 1 times the Heaviside function, and the Fourier transform of 1 is 1 over s. And by this shifting theory, then I have e to the minus s, as. Okay. Let's see this example. I have a Laplace transform sine times the shifted Heaviside function. First, we see, well, if we have a shifted Heaviside function, we may think about this theory. So first, let's just focus on the sine function. What is the Fourier transform of the sine function? This is a Laplace transform. If I want to use this theory, I also need to shift the function itself by a. So I need to shift the function by pi over 2. I see. Let's analyze this function first. Sine 4t. Since it is a sine function, we know if the sine plus 2 pi or minus 2 pi, the value is the same, right? So this is also equal to the sine of 4t minus 2 pi. And then I can put 4 outside. There will be t minus pi over 2. So this function is equal to t minus pi over 2. Okay, this is another t. All right. So sine t, if this is f, it is also equal to f of t minus pi over 2. So I can replace t by t minus pi over 2. So here we have sine 4, and t becomes t minus pi over 2. And the Heaviside function, the shifted Heaviside function, so I have this shifted unit by pi over 2. So I have e to the minus pi over 2s. Laplace transform of your sine 4t. And you can check the table again. Sine 4t here. So k becomes 4. Any questions for this one? All right, next question, next example. I have a function g. Can anyone tell me that if I have this expression for g, now I want to change this expression, I will write it down the g function in terms of the Heaviside function. So if I want to rewrite the g function to the Heaviside function, how do we write it? Anyone? In terms of the different conditions, I can use one line with the Heaviside function to express the same function here. No? Think about these conditions. When do I have the value? When t is greater than or equal to 2, I have a value, right? So this function is t squared plus 1, but I only have a value when t is greater than 2. Okay. And now I want to make a form of a shifted function times the shifted Heaviside function. If I want to find the this Laplace transform. So now I need the form of g t minus 2 times this shifted Heaviside function. So we need to rearrange the t squared plus 1 becomes t minus 2 plus 2 squared plus 1. In this case, we have t minus 2 squared and 4 times t minus 2 plus 5. And this is the Taylor series for this function t squared plus 1 about 2. And the next week we're going to talk about the series solution, and we'll also mention about this Taylor series. Okay. But here the idea is that I want to rewrite t squared plus 1 in terms of t minus 2 term. Now I have t minus 2 term, t minus 2 term. In this case, my g function becomes So t squared plus 1 will become here. T minus 2 squared and the Heaviside function. 4 times t minus 2 times the shifty Heaviside function. And then the Heaviside function itself. But we know that the Fourier transform of the Heaviside function is 1 over s e and times exponential term. So if I take the Laplace transform of g, I have Laplace transform t minus 2 squared h Heaviside function. Second term, Laplace transform t minus 2 times the shifty Heaviside function. And 5 so this becomes e to the minus 2s Laplace transform of t squared. 4 times e to the minus 2s Laplace transform of t. 5 times e to the minus 2s Laplace transform of 1. Okay. Any questions for this one? Now, since we learned the shifted theory, okay, the second shifting theory, and of course the inverse of the second shifting theory will be giving you the Laplace transform, then you can find the function in time domain. So here is the inverse of the second shifting theory. So every time if you see a function times an exponential term, then you may think about the second shifting theory. So your answer should have your original function delayed by a. And also I have a shifted Heaviside function along with. So this will be e to the e to the 4 t minus 2, because a is 2, times the shifted Heaviside function shifted by 2, because a is 2. And now you need to check the table if you are not familiar with the Laplace transform. But if you do this more, then you know what is 1 over s minus 4. This one 1 divided by s minus a, that will be e to the at. Okay. So here you have, you know that your Laplace transform is 1 over s minus 4. Then the inverse Laplace transform will be e to the 4t. So this is e to the 4t, but you times e to the minus 2s, so e to the 4t, t becomes t minus 2, times the shifted Heaviside function. Okay. So next one, you can do it checking the table. Okay, here is the table. And then please find your answer. Okay, what is the inverse Fourier Laplace transform of this term? Okay, the first 3 people who get the correct answer have the bonus points. So the inverse Laplace transform of this, and then I show you the table. Here's the question, and now let's see the table. There's a common mistake, right, and also a trick. So, okay, let's see. Remember that for the second shifting theory, my function also have to shift. Okay. So first, we observe what is A. A is 3, right? Then what is your Fourier transform? The original Fourier transform. This should be S divided by S squared plus 4 squared, which means 2 squared. No, plus 4, so 2 squared. So here you can see that S divided by S squared plus K squared is cosine. Right, so this is cosine. So this is cosine 2t. All right. Then your answer h t minus 3, right? And then you will say, oh, this is cosine 2t, so cosine 2t h t minus 3, right? Then compare to here. If you shift, if you want to use the second shifting theory, if you shift from the Heaviside function, your original function, you also have to shift. Okay, so here it should be cosine 2 t minus 3. All right. Any questions for this example? No. Then next one. First, I have a function, the forcing function f over t, and I express f over t in this expression. Again, anyone can tell me that if I want to use the Heaviside function, how do I re-express this function in terms of Heaviside function? Anyone knows that? How do I rewrite the? Yes, you have a microphone.
T times the Heaviside function of t minus 3.
Okay. So here I can rewrite the forcing function as t times t minus 3 because I only have value once the t is greater than or equal to 3. Okay. And now here you see that I have an equation, the differential equation, and I also have initial conditions. I can also apply the Laplace transform to find a solution. So if I apply the Laplace transform, okay, here you're okay because we just learned the Laplace transform over derivatives. But the right hand side, if I take the Laplace transform, here the right hand side so far just Laplace transform t times ht minus 3. If we assume that the Laplace transform of y is the capital Y of S, so here this is the first term, and this is the first term, and here the second term. Okay, and we just mentioned that, remember that you at least you need to know what is the Laplace transform of y double prime and also Laplace transform of y prime. And then right hand side like this, we say this is the equation 3.2. Now I need to deal with the Laplace transform of t times the shifted Heaviside function, and why this is here. First, we need to rearrange this function f. So t times h t minus 3. I want to have like a same shift in Heaviside function, also my original function. So suppose t becomes t minus 3. So I subtract the minus 3 times the Heaviside function this term. So I need to add it back. And therefore, the Laplace transform t times the shifted Heaviside function is e to the minus 3s Laplace transform of t. And also the second term, 3 times e to the minus 3s Laplace transform of 1. First term is here, second term. All right. And then we can plug in the initial conditions. So in the initial conditions to the equation 3.2, we have s squared y plus 4 times y over s that becomes then you can find your y. Then your y is (3s plus 1) divided by s squared plus 4 times e to the minus 3s. You can use the partial fractions decomposition to get 3 over 4 times 1 over s. And the second term, so this is the partial fractions decomposition. Then you can check the table when you do the inverse Laplace transform to find your solution here, 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 and here. So your solution will be the inverse Laplace transform of your y. The first term, there will be 3 over 4. 1 over s. We know that the Laplace transform of 1 is 1 over s. So here, if you take the inverse, and now I also have the e to the 3s minus 3s this term. So this should be ht minus 3. Second term, I have a cosine. Cosine 2t, but this t should be 2 times t minus 3. And the third term, 1 over s squared. There'll be t minus 3. And the last term, t becomes t minus 3 as well. Okay. So we have the common term, the shifted Heaviside function. So we can put it outside. Then if you rewrite that, rearrange this. We have 2t minus 6 cosine 2t minus 3 minus sine 2t minus 3 h t minus 3. Okay. Any questions so far? If you don't have any questions, then let's move on first, and you will do some exercise later. The next topic is called the convolution theory. And this convolution theory is very useful and common. And you will use that in the future, definitely. But the first time when you see this theory, you may think it's more complicated and also abstract. But you will see that why it is useful using convolution theory. By the definition, what is the convolution? We say f convolves g. This is the definition. I have an integration from 0 to t. And then remember, for this integration, we do d tau rather than t. So we keep the g function. And then for the f function, we flip and shift by t. Okay. This is a definition of the Fourier convolution. I keep the same function. One of the functions the same. The other function I flipped and then shift. Okay. Remember, here is d tau, not dt. Why don't we need to learn the convolution? Because if the convolution is defined, then we take the Fourier transform. Then we take the Laplace transform. When we take the Laplace transform, well, in this time domain, it looks really complicated. But when you take the Laplace transform, actually, you just need to find out the Laplace transform of each function and then do the multiplication. Okay, so convolution becomes multiplication. let's see why the convolution becomes multiplication. So first, let's see this multiplication. F times G. What is the Fourier transform of F? Integration from 0 to infinity, e to the minus s tau, f tau d tau. And then gs, integration from 0 to infinity, e to the minus s. This time not tau, we use different dummy variables, beta, g, beta, d beta. So combine these two integration. We have e to the minus s tau plus beta, f tau, g beta, d tau, d beta. Okay. And then let's change the variable. Now that tau equals, t equals tau plus beta, because here we have tau plus beta, so this becomes t. Then dt equals d beta. So for d tau, it is from 0 to infinity. But for d beta, now beta is from 0 to infinity, right? So when beta is 0, t is tau. So if I want dt, then my integral should be tau to infinity. And I have f of tau e to the minus s. Tau plus beta becomes t. And then I need to change beta. So there's no beta anymore. So beta becomes t minus tau. So here g of t minus tau dt and d tau. Then we change the order of the integration. Now we do dt first and then d tau. I want to do d tau first, then dt. So change the order. Change the order of integration. If I want to do d tau first, here you can see t is between tau and infinity. So if I do d tau first, and tau is from 0 to infinity, so my tau so far I will do 0 to t. Okay, because tau is less than t. So here should be 0 to t, e to the minus st, f of tau, g of t minus tau, d tau, and then dt. And since I changed the order, so here I show you This is d tau. And then since this is d tau, e to the minus st, this exponential term, I can put it outside. E to the minus st. And inside the integral is integration from 0 to t, f tau, g, t minus tau, d tau, and then dt. And you can see this term is just the definition of G convolve or convolute F. So this is Laplace transform of G convolve F. All right. Any questions of this one? So now you can see the convolution, the Laplace transform of the convolution will be the multiplication. And then if you take the inverse Laplace transform of the multiplication of two functions, then in time domain there will be the convolution. And why do we need to learn this? Because here is the example. If you check the table first, I cannot get this form, s times the something perfect square. Right here I don't have that. And I really don't want to use the definition to find the inverse Fourier transform. In this case, we can think about this probably has two functions. One function times another function. And this is 1 over s. And then the other one is 1 over s minus 4 perfect square. In this case, I have a 1 over s and 1 over s minus 4 square. 1 over s, we know this 1. And 1 over something square. Something square. Here. 1 over s square. Okay? So, in time domain, it should be 1 convolve t times e to the minus 4, e to the 4t. And then in time domain, this convolution, by using the definition of the convolution theory, then you will get 1 over 4 times t e to the 4t minus 1 over 16 e to the 4t plus 1 over 16. Any questions for this one? Here are some properties about the convolution. Okay, f convolves g equals g convolve f. It is the commutative law. And for the associative law, if I have 3 functions, you can pick either of 2 to do the convolution first, and then convolve the rest. Okay, they are the same. And distributive law, if I have still 3 functions and 2 functions, add them together, convolve the rest, the other one, then I can do the convolution first, followed by the summation. If I have a constant c, well, this constant c could be in the f function or g function, or later on you just put this c after the convolution. You still get the c here. So let's just do the commutative law. Y f convolve g equals g convolves f. So by the definition, f convolves g. If f convolves g, we keep the g, but the f I flip and shift. Okay. So now I just change the variable. Let's change the variable. Let's say z equals t minus tau. So this t minus tau becomes z, and tau becomes t minus z. Here d tau will be minus dz. Okay. So here we have f of z, g t minus z. We have minus 1 dz. And also tau is from 0 to t. And then how about z? So minus tau is greater than minus t, greater than 0. T minus tau greater than 0, here will be t. Okay, so your z is between 0 and t. So here we have 0 to t. So t to 0, t to 0. And then if I change 0 to t, I have t minus z dz. F of z dz. And that's why this is g convolve f t. All right. So now you know that f convolves g. Well, it doesn't matter which one is the first, because this is also equals to g convolves f. So now let's use this concept to find the solution of this following differential equation. Taking the Laplace transform first. Okay, so if you take the Laplace transform, we have s squared y minus s minus 2s y of s. Taking the Laplace transform of y double prime and y prime, you should remember it. Okay, we won't give you any hint. The right hand side f is just a function now, so we may say this is the Fourier transform of f of s. Then you can find the y. So your y using the partial fractions decomposition again, then you decomposed this fraction. Partial fractions decomposition. You get 1 over 6, 1 over s minus 4 times the f of s. The second term, third term, and well, sometimes you have the same differential equation without with different forcing function. So this forcing function is undecided. So far you can express your solution in Laplace domain with this form. And then later on, when you try to find the solution of y, here we see two functions times together in this domain. So when I take the inverse Fourier transform, it becomes a convolution. And then later on, you can plug in any kind of forcing function here. So the solution will be 1 over 6 e to the 4t convolves the f. The second term, e to the minus 2t convolves f. And the third term will be 1 over 3 e to the 4t. Last term, e to the minus 2t. Any questions for this one? We can also use the convolutions to solve the integral equations. So if my forcing function here, I have integration, then we can think about this integration is a convolution. And then when we take the Fourier transform, well, when we take the Laplace transform, well, this becomes a multiplication. Okay, so take the Laplace transform. We have 4 over s cubed. Okay, that's the first term. And the second term. The second term, f of s e to the minus t, there will be 1 over s plus 1. Well, in this case, we get f of s equals 4 over s cubed plus 4 over s to the 4th. Bring this here. And taking the inverse Laplace transform, then you have f equals 2t squared plus 2 over 3, 2/3 t cubed. All right. Any questions for this one? If you don't have any questions, then let's just move on. The next is the unit impulse. So, what is unit impulse? here is the definition. Okay, when t is between two values here, it's 0. Well, when t only between these two regions, I have a value 1 over 2a. Otherwise, it is all 0. So if I plot this function, it becomes here's t, and we have t naught minus a, t naught minus a, and t naught plus a. And then our value is 1 over 2a, so here is 1 over 2a. So I have a values between these two. This is, you can see this range is 2a. Okay, and when a becomes smaller, so they will shrink. So this point, the left ending point, will tend to t, and the right hand point also will tend to t. So it becomes smaller. So it could be. And also, when a is smaller, this value becomes larger, right? 1 over 2. Later on, 1 over 0.5, 1 over 0.01. So they will go up. So they may go up. And if it's more smaller, so for a smaller value of a, this function will become a constant function of large magnitude, because if a is smaller and smaller, they will go up. So this value will also go up. So we call that this delta a of t minus t naught unit impulse. And when I take the integration, which is the area of this region, okay, there will be 1. When a goes to 0, well, here we have a subscript a, okay? But when a goes to 0, which means I only have a point at t, so I have an infinite value, because when a is 0, it goes to infinity, right? When a goes to 0, then we will say that t equals t naught is infinity. Otherwise, the value is 0. Okay? And when we take the integration, we will say the integration from 0 to x is greater than t naught, t minus t naught dt. it should be 1 for x is greater than t naught. Because now I have a, this is t naught, I have a spike. Okay, it goes to infinity. But when I take the integration, I will find the value under that function. There'll be, we will say this is 1. And we call that, without a, if we have a as a subscript, it is unit impulse. But without that, we said this unit impulse is called a direct delta function. And if you take the Fourier transform, then this direct delta function is e to the minus s times t naught. Why? Here's the proof. So delta t minus t naught again, we have this function, right? Every time if you see these simultaneous expressions for a function, you can always use the Heaviside function to re-express this function. So what is the, how can I rewrite this function using the Heaviside function? I only have value between these two numbers. So I only have value, the value is 1 over 2a. Between that two numbers, so I have t minus t naught minus a. And the upper bound is t minus t naught plus a. Okay, t minus a, t naught minus, before t naught minus a I have here and here, 0. I have a 0 and then 1. But the second one, I still have a 0 when t is t naught plus a and I have a value 1. So that's why if I subtract, I only have a values between these two numbers. Okay. So the Laplace transform of this unit impulse will be 1 over 2a the Heaviside function. Heaviside function here we have e to the minus s t naught minus a. E to the minus s t naught plus a. So we got e to the minus s t naught 2sa and e to the sa minus e to the minus sa. When a goes to 0, because we want to shorten this width, okay, when a goes to 0, they become smaller, 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 and also the value go up, up, and up, increasing. So when a goes to 0, the denominator is 0. The numerator is also 0. Right, because 1 minus 1 will be 0. So it is 0 over 0. Okay, so this part. Then if it is 0, divide by 0, from the calculus, we can use the L'Hopital's rule. L'Hopital's rule. The Laplace transform of the direct delta function. That's that a goes to 0 of the Laplace transform of the unit impulse. So it is e to the minus s t naught limit a goes to 0 to SA. Okay, L'Hopital's rule, what is that? We take the derivative, the numerator and denominator separately. Okay, so this becomes, if I take the derivative with respect to a, in the denominator we have 2s. Numerator we have s times e to the sa plus s times e to the minus sa. And then we plug in a goes to 0 again. So a goes to 0, this will be s plus s will be 2s, here is 1. Then this limit is 1. We have e to the minus st naught. And when t naught is 0, then we can find the delta function. The Laplace transform of delta function is 1. All right, any questions so far? Here is just that give you the reason that why the delta function, the Laplace transform of the delta function is 1, and also the definition of the unit impulse. You will use this a lot when you take the signals and systems and also other advanced courses, okay? Because we have a filtering property. And what is the filtering property? If I have a function f and at times this unit impulse or direct delta function, when you do this integration, actually this is f of a, because I only have a value at a for this unit, for this direct delta function. So this is a very useful filtering property. Okay. If you do the convolution, f convolves this delta function, it is the function itself. Okay. Now, here is the differential equation, and the forcing function is the direct delta function. So if I use the Laplace transform, okay, this one, because I also shift, the Laplace transform of delta function is 1, and I shift by 3, so that's why we have exponential. Okay, so therefore we have y of s equals 1 divided by s squared plus 2s plus 2 e to the minus 3s. Every time you see this, check the table first. If you can make it as a perfect square or something, then we do it. So, and also the numerator is a constant, not s. So we can rewrite it as x plus 1 squared plus 1. Because we found the inverse Fourier transform, the inverse Laplace transform. Here is e to the minus t sine t. Therefore, this is t minus 3 sine t minus 3. Right. Remember that if I, in the Laplace domain, I have exponential term, that means it's high probability that in your time domain, I have shifted Heaviside function. And since it is shifted, my main function, I also need to shift by the same unit. Okay. A lot of people probably just write it down, the shifted Heaviside function times e to the minus t sine t. No. Any questions for this? If not, then let's see what is the derivatives of Laplace transform. Okay, so here you can see that I can also take the derivatives with the Laplace transform. And what is this? Suppose I have a Laplace transform. And then if I need to take the derivative of the Laplace transform, that means in your time domain, I times the t to the n. Every time when I times the t, that means in Laplace transform, I need to take the derivative. If I times t squared, then I need to do like 2 times. And here I also have like minus 1 for changing the signs. For example, if I have a t times f of t, that means the Fourier transform, Laplace transform. The Laplace transform, I will take the derivative and have a minus 1. So in this case, rather than using Euler formula or other methods, we can also take the Laplace transform to find a solution. Here, if I have a t times the y prime, then when I take the Laplace transform, y double prime here, t y prime and minus 4y, Laplace transform of 1 is 1 over s. So again, that you need to remember this is Laplace transform of y double prime. Okay. Let's deal with the second term. I have t times y prime. Laplace transform of t y prime of t. That is minus 1 to the, I only have 1 t, so the exponent is 1. D over ds f Laplace, we have t no, y prime. This is minus d over ds. What is y prime? The Laplace transform of y prime as y of 0, y of s minus y of 0. So that is minus y of s minus s y prime of s. So after the Laplace transform, we have s squared y of s minus 2y of s minus 2s y prime minus 4y of s equals 1 over s. If you rearrange this Laplace transform and you see that actually here it is also a differential equation, and this differential equation is which type? Separable, linear, exact, or any other special one? Apparently here you can see that this is the differential equation is what? This is linear. Since it is linear, then I need the integrating factor. So here is the integrating factor. E to the 3 over s minus s over 2 ds. That gives you e to the 3 natural log s minus s squared over 4, which is s cubed e to the minus s squared over 4. So you times this integrating factor, x cubed e to the minus s squared over 4 y prime, and here the second term I also need to times s cubed. Alright, let's do that again. S cubed e to the minus s squared over 4 s cubed e to the minus s squared over 4. This becomes minus 1 over 2s squared s cubed e to the minus s squared over 4. So the left hand side becomes s cubed e to the minus s squared over 4 y so you'll get y. This y is in S domain. So this is in S domain. That's e to the minus s squared over 4 plus a constant. So your y in Laplace transform domain, Laplace domain, there will be 1 over s cubed plus c over s cubed e to the minus s squared over 4. And here's the note. When s goes to infinity, and we have this property, this function goes to 0, so we can choose c equals 0. Then your answer is just 1 over s cubed. So when you take the inverse Fourier transform, you get your final answer. That is 1 over 2 t squared. All right. Any questions for this one? Why do we need to use Laplace transform? Here we have a system. We can use Laplace transform to find a solution as well. Okay, so if I take the Laplace transform, first equation, I have s squared x minus 2sx, because the good thing is that the initial conditions are all 0, okay, plus 3sy plus 2y will be 4 over s. And the second equation, 2sy minus sx plus 3y, that's 0. So you can find x and y. So your x is 4s plus 6 divided by s squared, s plus 2, and s minus 1. Using partial fraction decomposition, you have minus 7 over 2, 1 over s. And 3 times 1 over s squared, and 6, 1 over s plus 2, and 10 over 3, 1 over s minus 1. And your y will be 2 divided by s, s plus 2, s plus 1, s minus 1. And then since you get the expression for the x and y separately, then taking the inverse Laplace transform, you get x of t. Again, you can use the table. And also your y. Okay, so see, you can see the powerful of using Laplace transform. Just several lines that you can find the answer.